Hello again. Welcome to my home. I thought you might be interested in seeing how to solve the questions on the final. So this is going over the semester one final that was given out. Let's get started. What is the x-coordinate of the point of inflection on the graph of y equals 1/3 x cubed plus 5x squared plus 24? So if we're looking for points of inflection, we can do that. Generally, we're not interested in points of inflection just by themselves. If you are, you want to look at the second derivative. Oftentimes, and this is a point where people can get confused because oftentimes you're looking for points of inflection as a confusion when you're looking at the critical points. So again, critical points are where the first derivative is 0, and that could be either a max, a min, or a point of inflection where the first derivative is 0. If you're looking for points of inflection, there's a problem in that you can have points of inflection that are not maxes, that aren't critical points. You can have points where it's a point of inflection. So point of inflection is where the curvature changes. That isn't, the derivative isn't 0. And this picture is a good example. The derivative looks like it'd be some negative number. Obviously not 0, but it's still a point of inflection. So if we're just looking for point inflections, we need to go directly to the second derivative. So we have our function here. Our first derivative, dy dx, we'll just do it term by term. That's going to be 1/3 times 3, so just 1 x squared plus 2 times 5 is 10x, and then this goes away. So that's our first derivative. Second derivative, that's going to be 2x plus 10. And now if we're looking for point of inflection, we set that equal to 0. 2x plus 10 equals 0 when x equals -5. And now we're going to, we've done the calculus work. We want to check back to the original question. What is the x-coordinate? Oh, we're done. No more work has to happen. So we can move on. Next, we have a situation where it wants a definite integral from 1 to 2 of 1 over x squared dx. This, we're going to use our integral power rule. Generally, this is going to be your bread and butter for most integral problems, honestly. We're going to recast this instead of 1 over x squared. That's the integral from 1 to 2 of x to the -2nd power dx. And so now we think to ourselves, what is the antiderivative of x to the -2nd power? What is the function that when you take its derivative gives you x to the -2nd? Well, you can apply the power rule, but it's pretty easy to see that it's going to be, the power of it is going to be x to the -1st because -1 minus 1 is -2. And then to compensate, we have to divide by -1, which just ends up adding a negative in front of it. We then evaluate that from 1 to 2 by going -2 to the -1st minus -1 to the -1st. This becomes -1/2. This just becomes +1. -1/2 plus 1 is 1/2. And that will be our answer for this one. Moving on. This one is another integral, but it's an integral from the graph. So this one states we have a graph of a piecewise linear function, f. We stay its domain, so that gives you an idea of what this scale is. This is -1, this is 4. And we hope that scale still applies, so this would be -1, this would be 1, 2, that sort of thing. As shown above. What is the value of the integral from -1 to 4 f of x dx? Now, since this is piecewise linear, we're not going to use antiderivatives here. We're going to use our knowledge of areas. And generally, you can cut this up in a couple different ways. You could cut this up into just triangles and rectangles, if that makes you happier. Or you could think of it as this trapezoid and this trapezoid. Either way, no big deal. But the key thing to remember is that this is a positive area since it's above the x-axis, and this is a negative area since it's below the x-axis. I'm going to just do this by rectangles and triangles, just because it's easier. Area of this triangle, we've got base of 1, height of 2, 1f base times height, so that's going to be, if you allow me to recopy this here, this triangle's area is going to be 1, this rectangle's area is going to be 2, this triangle's area is going to be 1, this triangle's area is going to be negative 1/2. Again, negative areas, they happen in integrals, and then this rectangle is actually a square, so it's just going to be negative 1. So that's going to be 2.5, or 2.5. If you want to do this as a improper fraction, that would be 5/2. All these are acceptable. Probably go with that one just to start since it's easier. Great. Now we've got conditions. What conditions must be true? So this, we're going to need some words here. For the mean value theorem to apply for a function on, I didn't change this on this, an interval from a to b. All right, so for mean value theorem, it must be f must be continuous on, and this is semi-important, the closed interval from a to b, and f must be differentiable. So you are able to take the derivative on the open interval from a to b. And those two things must be true. So it's like two separate statements. You have to have both of them, because if you violate either one of them, mean value theorem does not apply. That's all we need for that. You just had to remember that those are the conditions. All right, so we've got a straightforward limit problem. If you're seeing this on an AP test, you can pretty carefully assume that it's going to come out to 0/0, but it's worth trying in this case just to see. We have -1 squared minus 5 times -1 minus 6 all over -1 plus 1. So obviously the denominator comes to 0. -1 squared is 1. We'd have 1 plus 5 minus 6. Well, that's 6 minus 6, which is also 0. All right, it's as we expected. It's 0/0, which is what's called an indeterminate form. And anytime you have this, that means there still might be a limit. We just have to do some algebra to see what it might be. In this case, where it's polynomial over polynomial, we should factor that numerator. So we want the limit as x goes to -1 of, let's factor that, x factors of -6, 1 and 6, or 2 and 3, worth one of them negative. We're going to have -5. We need to have +1, -6. Again, if you're doing this on the AP test, since AP, and this problem was made by a human being, me, the AP test problems were also made by human beings. You can be pretty certain that the factor in the denominator or numerator, whichever is applicable, there's going to be that factor in the other side of the fraction, right? They're not going to set it up. There actually isn't a way to set up where you get an indeterminate form and it doesn't share a factor. So you can, if you need help factoring, know that when you have a situation like this probably has a factor of x plus 1. And that allows you to figure out what the other one is pretty quickly. In the limit, those cancel, and you get the limit as x goes to -1 of x minus 6. -1 minus 6, that's -7. There we go. All right. Now, we have an implicit, well, we have another function here. If x squared plus xy equals 10, then when x equals 2, what is dy dx? Now, there's two ways of going about this. One is to take the derivative implicitly and plug some stuff in. And the other one is to do some algebra first. Generally, you're going to have to do some algebra with these. The question is whether you want to do it before you take the derivative or after. Since this is a demonstration, I'm going to show you both ways. So let's start with taking it implicitly, because that's probably what most of you are going to have some struggles with. So taking it implicitly, we get 2x plus, and here comes the trick, this is a product, we need to use the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first, which is 1, equals 0. And at this point, we have x, we want dy, but we don't know what y is, so we actually have to go back to our original function to figure out y. When x is 2, you have 4 plus 2y equals 10, which means that 2y equals 6, y equals 3. And so we say, oh, all right, so we have 2 times 2 plus 2 times dy dx plus 3 equals 0. Dy dx equals -7. Some algebra in those intervening steps. So that means dy dx, what we're looking for, is going to have to be -7/2. Cool. So that's where we take the derivative first. We're very eager, so we take the derivative first and do the algebra later. Now let's say we didn't want to do that. We want to take our hits on the algebra in the first part. Well, that's no big deal in this case. In some cases it is a big deal. In this case it isn't a big deal. We just take our original equation here and start solving it for y like we would do any other place. So you get xy equals 10 minus x squared. When you divide both sides by x, y equals 10 over x minus x. And you can leave this as just, you can have it as 10 minus x squared over x as a fraction. It's going to be easier to take the derivative this way, because when it's this way, you can take the derivative term by term. So derivative of y is, of course, dy dx. Derivative of 10 over x is going to be -10 over x squared. And the derivative of x is just 1. You plug in 2, you get that dy dx equals -10 over 4 minus 1, which becomes -5 over 2 minus 1, which we can see pretty easily. That's -7 over 2, like we had on the other side. No big deal. So again, there's always choices in how you want to solve these, and you want to go with whatever's most comfortable for you, because anything that's outside your comfort zone is going to take more effort and more mental tax. So if you're really comfortable in implicit differentiation, maybe this is the way you go, because like, oh, you see it like this, oh, it's an implicit differentiation, just follow your nose on that one. And maybe you're like, oh, I don't really like doing that. Well, then it's time to put in the work in the first part to solve it, and then if you do that, you'll find it's really not that hard either way. Okay, this one I got. Most of you got this, but I'm still getting some people. Whenever you see definition of something where it's bolded and italicized, you need to go back to what I told you was the definition of things, right? So we're not using any of the rules we developed. We go back to like the bare bones, and it's going to involve a limit. So remember, the definition of the derivative of anything, if our y equals f of x, the definition of derivative of that is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, right? This is the definition for any function. To be fair, there are alternate definitions that are essentially variations on this, but this is the one you want to commit to memory the most. So in this case, our f is going to be 7 to the x, right? So anytime you see x plus h here, you replace that there. So our definition of the derivative is going to be the limit as h goes to 0 of 7 to the x plus h minus 7 to the x over h. And that's all I wanted. If you can remember the definition of the derivative, which I hope you can, these problems should be pretty easy because they don't require any computation. All right. Let f and g be differentiable functions with the following properties. So we're going to have to think about it on this one, just a little bit. So we're saying that g of x is always positive for all x. So, okay, so it's always positive. The key things is that g of x, if this is the case, is never equal to 0. That's going to be important later. But 0 is a trouble. So when they make so much effort to say it's greater than 0, the important part isn't necessarily the greater than. The important part is that it isn't 0. And then it tells you that f of 0 is equal to 1. Okay, great. Now we define a third function, h, which is the product of the two other functions. And then we give the derivative of h, and it has this particular thing. And they want us to know what is f of x. Well, this is hard to think through cleverly. So let's not be clever. Let's be stupid. All right? And if we're following this, we're like, oh, we have something with h, and we have something with h prime. What is the only relation we have through this? Like, after a little bit of thinking, well, we have our derivative rules. There aren't that many. We're supposed to remember them all. Which one applies here? And again, we're just trying to match this, right? And if we're trying to match this, we have f times g. Well, that's the product rule, because it's a product of two functions. Well, let's apply the product rule. If we apply the product rule, h, that's the first, so f of x times the derivative of the second, g prime of x, plus the second, g of x, times the derivative of the first. Now again, we're not, say hello to Arthur, everyone. Hey. All right. Thanks for that interlude. This is obviously, like, it's mostly the same. In fact, this one matches up exactly. So this is the same as this. But somehow they managed to get rid of this, right? Well, what's the only case where you can leave off an addition and it just doesn't appear? Well, if that equals 0. So this has to be 0 at some point, or at all points. Well, and this is why I made the special emphasis earlier, they told us that g of x is never 0. It's always positive. So this is not equal to 0, which means that this part, the f prime, that is equal to 0. Well, okay, so f prime equals 0. If f prime equals 0, what is f? Well, the only thing we know whose derivative is 0 is some constant. So f of x has to be a constant. Is that enough? Now, some people got to this point and they stopped and they're like, oh, it's a constant. Well, yes, it's a constant, but it's a very specific constant. I did give you the information to figure this out. Let's look back to the start. Oh, f of 0 is 1. Well, if f is constant, then it's always 1. So f of x is just 1. Always and forever. So always make sure, in these problems, make sure you're using all the information given, because there's very few cases where completely extraneous information is given. In this case, both of these bits, or I guess all three of these bits, this bit, and this bit, are needed to solve the problem. All right, this is the last one on this video before we turn to the next 2 pages. All right, this is a graph and word problem. The flow of oil in barrels per hour through a pipeline on July 9th is given by a graph shown above. Approximate the total number of barrels that pass through the pipeline that day using the trapezoidal rule on 4 equal subintervals. So the 4 equal subintervals is kind of important. We see, and I kind of did this for you already, that when you cut this into 4 equal pieces, well, those are just going to be on the graph lines. And when you turn them into trapezoids, well, these are going to be actually kind of boring trapezoids. But the point isn't to make, there's only so much interest you can get in trapezoidal rules. So it's not a big deal that it's boring. The last thing is to remember that the widths of these trapezoids are 6. They're 6 hours each time, right? So this rectangle and this rectangle have an area of 6 times 100, so 600 barrels. And this trapezoid and this trapezoid, they each have, so 150 times 6, 3, 900. So these both have an area of 900 barrels. And when you add them all up, 1,800, 1,200, 3,000. Unit on that is barrels. Barrels of oil, doesn't really matter. But yeah, and again, this is area. No one's stopping you if you can't remember the formula for the area of a trapezoid, of just cutting this into a rectangle with a triangle on top. No one's stopping you. No one can tell you no. But yeah, just straightforward, cut it up as it looks like, according to the number of subintervals, draw connecting lines, and find the errors. That's how you solve a problem like that. And I think that's it. It is. Well, thanks for stopping by, and I'll have the rest shortly, I think.